The first scheduling method, critical path method, will be discussed in this video. Critical path method, or CPM, is also known as network diagram analysis. It is a systematic approach to scheduling project activities, identifying the most critical tasks, and ensuring timely project completion. CPM is a scheduling technique that uses a visual representation of a project's tasks and their interdependencies. To understand the method, first, we will explain the concepts of serial activities, concurrent activities, merge activities, and burst activities of a project. Serial activities. Serial activities are those activities that flow from one to the next in sequence. Following the logic of the figure shown here, activity A can begin immediately. However, we cannot begin activity B until activity A has been completed. Activity C cannot begin until both activities A and B are finished. Concurrent activities. In many circumstances, it is possible to begin more than one activity simultaneously. When the nature of the work allows for more than one activity to be accomplished at the same time, these activities are called concurrent activities. When concurrent activities are available, parallel project activity paths are constructed through the network. The figure shows an example of how concurrent or parallel project paths are represented in an activity network. We can start activity C immediately. Activities D and E can begin following the completion of activity C. Activity F can start following the completion of activity D and is independent of activity E. Activity G can start following the completion of activity E and is independent of activity D. Activity H can begin following the completion of both activities F and G. The next concepts, merge activities and burst activities. Merge activities are those activities with two or more immediate predecessors. The figure illustrates a partial network diagram that shows how merge activities are expressed graphically. The logic of this merge activity tells us that we cannot begin activity D until all predecessor activities, A, B, and C, have been completed. The start of the merge activity is subject to the completion of the longest prior activity. For example, activities A, B, and C start on the same day. Activity A has a duration of 3 days, activity B's duration is 5 days, and activity C's duration is 7 days. The earliest day activity D can start is on day 7. Burst activities, on the other hand, are those activities with two or more immediate successor activities. Here, the figure graphically presents a burst task. Activities B, C, and D are scheduled to follow the completion of activity A. All three successors can only be undertaken upon the completion of activity A. All immediate successors can begin simultaneously upon completion of the burst activity A. Now, we are going to discuss labeling nodes. Project activities are represented by nodes. Each node should be clearly labeled with several pieces of information. A node may contain 8 pieces of information as shown in the figure: identifier number, activity descriptor, activity duration, activity float, earliest start time or EST, earliest finish time or EFT, latest start time or LST, and latest finish time or LFT. These 8 pieces of information are all related to a specific activity. Now we will be discussing how we can identify and sequence project activities. We will use an example of new website development to apply the concepts of successor and predecessor activities to create network analysis. The first step in project scheduling is to identify all the project activities. Next, we need to determine the sequence of all activities. The table identifies 6 activities and their predecessors in developing the website. The first activity A shows no predecessors. It is the starting point in the network and is placed to the far left of our network diagram. Activity A is the predecessor of both activities B and C. Predecessor means activities B and C can only start after activity A is complete. Activity B is the predecessor of activity D, and activity C is the predecessor of activity E. Finally, activities D and E are the predecessors of activity F. In this way, using the information in the table, we created the network by adding all activity nodes, as shown in the figure. This network begins with a single node, activity A, and concludes with a single node, activity F. In this network, Activity A is a burst activity because it has two successors, activities B and C. On the other hand, activity F is a merge activity because it has two predecessors, activities D and E. We will continue with our website development example and estimate the duration of all project activities. Once we have the estimates of all individual activities, we will be able to calculate the total duration of any project. In our example, we have a total of 6 activities. Estimated durations of these activities are presented in the table. We update the network diagram with durations labeled for each of the 6 project activities. For example, in the Activity A node, we have written its estimated duration as 5 weeks. Activity B takes 5 weeks to complete, Activity C takes 6 weeks, and so on. Each network diagram is likely to have multiple paths. Paths are like routes. Each path is discovered by assessing all possible sequences of precedence activities from the beginning node to the end. If we carefully analyze the network, we will find there are only 2 different paths of our routes from the beginning node, Activity A, to the end node, Activity F. Path 1 is A, B, D, F, and Path 2 is A, C, E, F. Now, we will learn how to estimate total duration of the project. We can calculate the length of each path of the network simply by adding their individual activity durations. From our website development example, we can see there are 4 activities in Path 1. So, the total length of Path 1, A, B, D, F, is 18 weeks. That is the sum of 5 weeks, 6 weeks, and 2 weeks. In this way, we can also calculate the total length of Path 2, A, C, E, F, that is, to 22 weeks. The longest path in the network determines the total time needed to complete a project. In our example, Path 2, which links the activities A, C, E, F, has an estimated total duration of 22 weeks. It is the longest path in the network, and this is the critical path of the network. Hence, the project is expected to be completed in 22 weeks. The critical path of a network has no float or slack time. Float informs us of the amount of time an activity can be delayed and still not delay the overall project. If it takes more time to complete any activity within the critical path, then the total length or duration of the project will increase accordingly. Constructing a critical path requires a forward pass and a backward pass. The forward pass starts from the first activity. It is an additive process that calculates the earliest times an activity can begin and end. The backward pass starts from the last activity. It is a subtractive process that gives us information on the latest times the activities can begin and end. Once both the forward and backward passes have been completed, we can also determine individual activity float and finally the project's critical path. Let's discuss how we can estimate earliest start and finish time. We will now add more information to the network by conducting a process known as forward pass. This will help us determine the earliest time each activity can begin and the earliest time each activity can be completed. Consider the website development example. The beginning activity A can be started at time 0. That is immediately. The estimated duration of activity A is 5 weeks. Therefore, the earliest we can finish activity A is on week 5. The earliest finish time, EFT, for any activity is found by taking its earliest start time, EST, and adding its activity duration, which is EFT equal to EST plus duration. Activity B depends on activity A, because activity A is the predecessor of activity B. The earliest we can start activity B is upon the completion of activity A, that is, after 5 weeks. Hence, the earliest start time, EST of activity B, is 5 weeks. The duration of activity B is 5 weeks. So, the EFT of activity B can be calculated by adding the EST of activity B 5 weeks and the duration of activity B 5 weeks, which gives 10 weeks. In a similar manner, we can determine the earliest finish times for activities C, D, and E. The EFT of activity C is 11 weeks. The EFT of activity D is 16 weeks. And the EFT of activity E is 20 weeks. However, during the forward pass process, we encounter a challenge at activity F, as it serves as the merge point for both activities D and E. As we know, the earliest finish time, EFT, of a predecessor activity is the same as the earliest start time, EST, of the successor activity. The challenge with activity F is that it has two predecessor activities. The rule to resolve this is that the successor activity can only begin once all preceding activities have been completed. Since activity E has the greater EFT, 20 weeks, we select 20 weeks as the EST for activity F. Therefore, the EFT for activity F is calculated as 22 weeks, that is 20 weeks EST plus 2 weeks duration. Once we have labeled each node with its EST and EFT values, the forward pass through the network is completed. The figure illustrates the overall network with the forward pass. Now we will learn how to estimate latest start and finish time. In order to calculate the latest start and latest finish times of all project activities, we will carry out another process known as the backward pass. The backward pass is an iterative process, just as the forward pass is. The difference is that we begin the subtractive process at the end of the network with the final node. In the context of our website development example, we begin the backward pass with the last node, activity F. The earliest finish time, EFT, and latest finish time, LFT, for the last node of any project will be the same. From previous discussions, we already know that the EFT for activity F is 22 weeks. So, LFT for activity F is also 22 weeks. Now, the latest start time, LST for activity F, is the difference between the LFT, 22 weeks, and the activity's duration, 2 weeks. So, the LST for activity F is 20 weeks. These values are shown at the bottom of the node. Activities D and E are the immediate predecessors of activity F. In order to determine the LFT of these two activities, we will carry the LST value of activity F backwards to these nodes. Therefore, activities D and E will each have 20 as their LFT value. Now, in order to get LST for these two activities, we will subtract their respective durations from their LFT, which is 20. Hence, the LST of activity D is 14 weeks, that is 20 minus 6, and the LST of activity E is 11 weeks, 20 subtract 9. In a similar manner, we can determine the latest start times for activities B and C. The LST of activity B is 9 weeks, and the LST of activity C is 5 weeks. Activity A has multiple successor activities, making it a burst point. This presents a challenge in selecting the correct latest finish time, LFT. The successors of activity A are activities B and C. To determine the LFT of activity A, we apply the rule that requires selecting the lower latest start time, LST, of the successor activities. In this case, the LST values of activities B and C are 9 weeks and 5 weeks, respectively. The lower value, 5 weeks, is chosen as the LFT for activity A. Therefore, the latest start time, LST, for activity A is calculated as 0 weeks. That is, 5 weeks LFT minus 5 weeks duration. Once we have labeled each node with its LST and LFT values, the backward pass through the network is completed. The figure illustrates the overall network with the backward pass. The last topic to discuss from CPM is estimating the floats. Once we have found the earliest start time, earliest finish time, latest start time, and latest finish time, we can determine the float, or slack, for each activity. Float informs us of the amount of time an activity can be delayed and still not delay the overall project. Activity float is found by using any one of these equations. Float equals latest finish time minus earliest finish time, or float equals latest start time minus earliest start time. Using these equations, the float of activity B is 4 weeks, that is 9 minus 5, or 14 minus 10. Similarly, the float of activity D is 4, which is 14 minus 10, or 20 minus 16. In the same way, floats of activities A, C, E, and F are found to be 0 weeks. The project's critical path will always have a float of 0 weeks. This means that the critical path is the network path with no activity slack or float associated with it. In our project, we can determine the critical path by linking the nodes with no slack, that is A, C, E, F. The figure shows the complete network diagram of the project.